211% yield, the last section in the Foundations in Chemistry Part 2 unit. Wrapping up the outcome, use stoichiometry to determine the relative amounts of substances consumed and produced in a chemical reaction. We will be learning how to compare theoretical yield and actual yield for a variety of chemical reactions by calculating the percent yield, explaining how actual yield differs from theoretical yield using the concept of sources of error, and predicting how to maximize the yield of a particular chemical process. Theoretical, actual, and percent yield. Theoretical yield is the maximum amount of product calculated using the balanced equation. Actual yield is the amount of product obtained when the reaction takes place, and percent yield is the ratio of actual yield to theoretical yield. Percent yield is equal to actual yield in grams over theoretical yield in grams times 100. This is particularly useful for a lot of applications. If you're working in industry, you want the highest percent yield that you could possibly get. If you're working at the potash mine, you don't want to be losing potash. You want, if you did a reaction to extract potash from the particular ore, or if you're doing another chemical reaction in industry, you want to make sure you're getting a very, very high percent yield. You want like 100%, as close to 100% of the product being obtained as possible. Now, that's not always attainable, depending on the circumstance, but that's what people in industry really work to perfect their processes, so they're not losing a lot of the product to, like, maybe if you're filtering it, some of the product gets washed away, or maybe some of it, all of it doesn't react for a particular reason. So it's really important to get that high percent yield because, like we said, often when you're reacting two things together in a lab, you'll get not exactly what the yield is that takes place if you calculate it out on your piece of paper like we've been doing up till now. If we actually took one of those reactions in the lab, we might have a lower percent yield because some of it got lost, like I said, when you're filtering the product or transferring the product from one beaker to another. Quite a few different, some of it's stuck in the bottom of your beaker, you can't get it all transferred. Or a variety of, your product, your chemicals that you're reacting in the first place aren't super, super pure. There's lots of different ways you can get a lower actual yield, which corresponds to a lower percent yield. Or if your product isn't dry enough, sometimes there's lots of water left in your product. If you weighed your product, it would actually weigh higher than your theoretical yield because the water weighs more. And then you might get a higher percent yield than even 100% because you're weighing actually some water. Your product needs to dry out a little bit better before you weigh it. When we're calculating percent yield, the actual yield and the theoretical yield are needed. If we prepared cookie dough to make 5 dozen cookies, the phone rings and you answer. While talking, a sheet of 12 cookies burn and you have to throw them out. The rest of the cookies are okay. What is the percent yield of edible cookies? You, in theory, should have had 60 cookies, but you can only eat 48 cookies because of those 12 that burnt. Your percent yield would be 48 cookies divided by 60 cookies times 100, which is 80% yield. So how do we do this with stoichiometry? Without proper ventilation and limited oxygen, the reaction of carbon and oxygen produces carbon monoxide. If the percent yield of 40 grams of carbon monoxide are produced what is the percent yield if 40 grams of carbon monoxide are produced when 30 grams of oxygen are used? Well, 40 grams of carbon monoxide are actually produced. When we started with 30 grams of oxygen, we're starting with 30 grams of oxygen. We need to figure out how much grams of carbon monoxide we could mathematically produce, and then use our actual yield divided by our theoretical yield to get our percent yield. So With our theoretical yield, we'll start with 30 grams of oxygen. We use the molar mass to convert to moles, and then our molar ratio to right here, and then convert back to grams with carbon monoxide. We get a 52.5 grams of carbon monoxide, which is our theoretical yield. Remember, theoretical yield is like how much in theory, if everything was perfect, how much could we, how much product could we attain? Or how much product could we get through math? Because again, like everything isn't always perfect. So how much does the math say that we should be able to produce? Because we actually produced 40 grams of carbon monoxide, but in theory we should have produced 52.5 grams. We go 40 divided by 52.5 times 100. We have a percent yield of 76.2%. And another example here, when nitrogen and 5 grams of hydrogen are mixed, the reaction produces 16 grams of ammonia. What is the percent yield? So this reaction actually produced 16.0 grams of nitrogen when we started with 5.00 grams. We need to figure out how much ammonia we, in theory, could produce from 5 grams of nitrogen. We do so using stoichiometry. We start with our hydrogen, convert to moles with our molar mass. We use our molar ratio to convert to ammonia, and then use our molar mass of ammonia to convert to grams. We get a theoretical yield of 28.2 grams. Our actual yield was 16 grams. We divide it by our theoretical yield of 28.2 grams times 100. We get a percent yield of 56.7%. There we go, percent yield.